Hi, this is Professor Stugard, and in this video we're going to discuss modeling. So our goals for this lecture, first of all, we want to understand why it is that we actually create models to begin with, and then we're going to talk about some key components of linear functions, because our first models are going to be linear models. And then we're also going to talk about some of the limitations that arise from doing modeling. So first of all, well, why do we create models? Well, given a data set, we want to create a model based on that data set, usually for two reasons. The first is to try to explain relationships between the variables, right? Figure out how are these variables related in some sort of way, if there is a relationship at all. And then, if we understand the relationship, what we really want to do with our model is to be able to make predictions. So, based on the data, create a model, and then use that model then to predict what might happen for other values. Now, what we want to do with our models is, if we can, hopefully create some sort of relationship between those variables that can be described with a function. So a function is our mathematical concept, which is where we take an input or multiple inputs and we run it through our function, which is our set of instructions, and then at the end it'll output a result for us. And the output of that result is our prediction in this case. So we're going to have our inputs, we put it into our function, which is another name for our model, and then arrive at our prediction at the end. So let's take a quick look at functions and how we represent them in math. So for example, let's say I was given the function f of x equals 3x plus 1. So the input here is x. That is my input is going to be my variable, meaning I can input whatever I want in for x into my function, which is called f. And then my output is going to be the results of, well, 3x plus 1, or 3 times x plus 1. So, for example, if I had f of 5, well, I take my variable x, and I'm now going to replace the x with the, well, number 5. And when I replace it with the number 5, well, on that right-hand side, now it's just a numerical operation that I can run. And 3 times 5 is 15, plus 1 is 16. So f of 5 is 16. And so when I input 5, I get 16 as a result at the end. And so I have this relationship between my input and my output that is actually described by my function. Now, this is a linear function that has a slope or a rate of change of 3. And again, we're going to start with linear functions because they are the most simple to work with and hopefully the easiest to understand as well. And when we talk about linear functions, every linear function has that y equals mx plus b form. Or if we're using the function notation, the more mathematical notation, it's the f of x equals mx plus b. And again, we typically prefer that function notation because we can see the input and the output at the same time. And again, it also speaks to the way that we've written our programming languages in a very mathematical sense. Now again, when we have that y equals mx plus b, m is your slope or your rate of change. That is really the core component that describes the relationship between those two variables. And again, in a linear function, that is describing how the variable y changes scaled upon the variable x, right? How my input x scales to determine my output y, and then b is my y-intercept, which again adds the up and down to it. Again, it doesn't necessarily represent it's not representing the scale or the slope or the rate of change, which again, rate of change, how does one variable change in relationship to another variable? But it is important for making sure we have our kind of our baseline set up. Now, again, going back to the main concept, we hope that our model will describe a pattern. Hopefully that pattern exists. Hopefully we can quantify it with our function, and then hopefully we can use that pattern to make predictions about the future. However, it is important to recognize that, again, our model is never going to be able to perfectly predict what's going to happen. There's too much chaos, there's too much random chance to actually have that be a realistic goal. But again, hopefully we can create a useful model that can guide decision making that works most of the time. And again, there's a little bit of probability that gets added in there as well. How probabilistic is it that our pattern that we've looked at creates a usable function? How often will that usable function create good predictive results? So again, we're going to be exploring data. We're going to try to describe the pattern in the data, All right, and then once we describe the pattern in the data, hopefully we can write a function mathematically to explain that pattern in the data and then use that to make our predictions. So there's, well, lots of different types of patterns when I look at data. So again, this one is pretty straightforward. All those dots are really in a straight line, which means I can represent that with a linear function or a linear pattern or a linear model. And again, we can kind of use all those words interchangeably here. And again, that's what we're going to focus on first because it's hopefully the kind of the easiest to really understand the concepts here. But that's not the only way that data is organized. So in this pattern, it is definitely a nonlinear pattern. We have more of a polynomial pattern. It's kind of going down and up and leveling off. And again, we can find that pattern in my scatter plot here. And it's not a linear pattern, but the pattern still exists. And it is important to recognize that a linear function might not describe this data so well, whereas, again, some other linear model would do a much better job. Now, making sure we have the definitions down as well. So we have our response variable. So again, our response variable is the variable whose behavior it is we're really trying to understand. Our response variable is our dependent variable on our vertical axis or our y-axis. Again, it is the dependent on the other ones. Our response variable, and again, we do say just one variable because, again, I just want that as my output. Then we have my explanatory variables. Now, again, sometimes it's just one, and again, with a linear function, maybe it's just one variable, like the x variable. But again, it's the variables that we're trying to use to explain our response variable. All right, and again, typically, if we're modeling, we put those along our x-axis. That's our independent variables. And again, if there is a relationship between two variables, remember, we can't necessarily claim that one causes the other in almost every case. We can't claim causation. We can just try to explain that there is some sort of relationship going on. But we can use some human intuition to hopefully point us in the right directions of maybe explanatory and response. But again, just kind of recognize that those are the two terms that we're going to use to describe typically what goes along the y-axis, our response, as opposed to our x-axis, our explanatory. And then again, when we do have a function or a model that, well, does our predictions for us, our predicted value is that output of our model function. All right, so we plug our data in, we plug our explanatory variables in, we're going to get our response variable as our output, and that is our predicted variable. All right, that is our output of our function. Another important concept is our residual. So once we create a model, our residual is a measure of how far our prediction is from what actually happens. All right, so again, let's say I have a bunch of points that seem to be in a line, and I draw that line there. Well, the points aren't exactly on the line, which I represented with the blue. Those blue lines are what we call the residuals. All right, and we measure how far away from our line they are. So our line, right, that's our prediction. Our line is our model, it's our function, it is our prediction of what's going to happen. Now, our actual data is not going to be on that line exactly. Like I said, it's a messy, random, chaotic world. But we need to capture how far off our model is. Again, we know we're not going to be perfect, but how close are we? And that is measured by our residuals, how far away from the line we actually are. Our residual is found by taking our observed value minus our predicted value, and always in that order, which means our residuals can be positive or negative depending on whether they are above or below our model, above or below our prediction. So again, that's how we find our residuals. Now, when our modeling function gives us our expected response, again, like I said, there's many different types of models. We're going to stick with linear models to begin with because, again, the whole reason we do this modeling is that they can sometimes reveal patterns that aren't necessarily evident in the graph of the data. So again, we can have a scatter plot, and the ones we've looked at are kind of obvious that there's some sort of pattern in there. We can use modeling to hopefully come up with a pattern, or it'll come up with a function for us, and then we might not have seen that pattern ourselves, but again, it still was in there in the data and can, again, hopefully help us to understand that data better, to make our predictions, to understand those relationships between our variables. So again, modeling is really, really important because it helps us sometimes see patterns, or I guess I should say helps us find patterns that we don't necessarily always see at first. However, there's also a really, really big risk that when we create our model, it's actually just imposing structure that doesn't really exist, because it's going to come up with the model no matter what. If we tell it to come up with a model, it'll do it because it's a computer. It'll do exactly what we tell it to do. And we might even think that that's a good model and based upon our small data set. But that doesn't necessarily mean it's actually going to be a good predictor. It doesn't mean that it's a good model. So again, there's trade-offs. There's a lot of value to it, but we need to be cognizant at the same time that just because we come up with a model or a pattern, it doesn't mean it's always going to be great. We should always approach this with a skeptical mind. All right, we should always be a little bit skeptical of our model. Does our model work? Well, let's check it first. Let's be skeptical before we say that we've, come up with some great new prediction algorithm. All right. So, can you answer the following questions on our little introductory video? First of all, what are the two main reasons we create our models? Next, what are the two core components of a linear model? And then the last question, will the models we create, are they going to be perfect prediction machines? But again, hopefully they're useful, right? So again, make sure you can answer those couple of questions. Hopefully we learned a little bit in this brief introduction. And as always, take care of yourselves.